So hi everyone, I'm Bart from Confio, and I will talk a bit about Cosmos Smart Contract basics, basically. There was the idea to do some live coding here, but I would go through because I don't have my laptop here, some technical issues, but it's fine. So there is a repository on my GitHub, HackATOM CW workshop. You can follow me there. I would show you how the basic system, based on two smart contracts, can be created. But first, let's talk a bit about the design. What the contracts are doing here. I figured out the idea for sharing donations, for example, between some some creators. Let's imagine we have a group of creators who want to increase their donators pool by, teaming up together. So if someone is donating one of those creators, donations are split according, depending on how much the creator is active, basically. So to achieve that, I created two smart contracts. And one contract is a peer contract, which is basically a single contract per creator. And the purpose is, there are two purposes of this contract. One is that there would be funds to withdraw by the creator who is attached to this peer. And also, if someone would like to donate on behalf of this creator, he uses this peer contract to donate. And how it works is when the peer is donated through, it increases internal counter, so he would get bigger rewards from other donations. And the other contract is the manager contract, which manages a couple peers or many peers. It is basically the pool of creators who are working together. And I am trying to keep this contract simple, so everyone can join to this peer pool. Everyone can leave at any moment, and you can also. There is also a donate function, but this donate function would not be called by some people who would like to donate the pool. It is only to be used by the peers. So when someone donates to this pool, he does it through the peer. Peer does its job, and then it forwards the call to manager. So this is roughly how contracts are structured. And we have a couple flows implemented. The join flow, very simple one. So creator is trying to join to the pool. I'm not sure if it's visible. Maybe enlarge it a bit. Okay. Okay, I cannot enlarge it. Anyway, so if creator wants to join to the pool, he calls join to the manager. Manager creates new peer for him and registers in internal map. And the idea is that manager needs all the peers registered for two reasons. One is to split donations after some distribution. And also, we need to keep information who already registered to the pool, so he doesn't register twice, for example. Leaving the pool is very simple. Creator just leaves the pool and peer is removed. And you can see that when joining to the pool, the peer is created, but it's never destroyed. We never destroy contracts, they are living there forever. But because the peer pool is removed from the map in the manager contract, it would be just useless because it would be impossible to donate through this peer or receive any donations. And here is the most interesting flow, which is donating. So how do we donate funds? Maybe let me read this. From the left there is donator, one peer, manager, and two other peers. So what happens? When we donate to the first peer, First, some funds are sent to manager. I say some because the contract is kind of smart, and if we donate on behalf of the particular peer, some funds are left directly on the peer, and rest are just split. Then the manager is querying for how many donators are on the particular peer, and it's done for every peer contract. So it's here, here, and here. And then every peer is responding with donators count. And after this donation count is basically retrieved from peer contracts, we send funds from the manager pool to particular peers. And you may see that there is not the best design because we are sending money for every peer, and basically we could send them directly probably to creators. That's true. The reason is to show how to communicate between contracts. That's the idea here. Okay, so this is the flow, and the last flow I have here implemented is I think pull withdrawal. So when we withdraw something from the peer, we need to be, the sender of the message has to be an owner of the peer, which he is assigned on creation. And then peer just queries its balance and gives back all the money to the creator. So very simple flow. And now I would like to talk a bit about how smart contracts are communicating, not looking at the code just yet. This is, I think, the most difficult thing to understand while creating smart contracts. I'm talking about IBC, which is kind of another story, but in terms of working with on single chain contracts, communication between them is kind of tricky. So there is this actor model, and the idea is that every message which is processed by the contract from the beginning to the end, and the processing of the single message can never be interrupted. No other contract can be directly called. We can do queries for another contracts while working on, while executing some message, but we cannot actually execute other contract. And this brings problems because what if, for example, I need to, let's say this joining flow. What I need to do, I need to create the contract first, another contract, so I need to execute the instantiate execution. But I cannot store the address on the manager contract state unless the instantiation is finished. So I need to call instantiate while executing this join flow. So there is this notion of reply. So what does it mean is when we send some message to the blockchain from the contract, because every contract can basically schedule another messages to be processed after the execution is finished. So like here, for example, we have some free contracts, free abstract contracts. We have blockchain here, which is the contract binary, I would say, just some magic thing which is executing the blockchain, and here is the message sender. So when we send to execute the message on the blockchain would send this message to the contract, because here I'm executing some message 1 on the contract 1. So message 1 is sent to contract 1. What happens now? Message 1 is processed from the beginning to the end, and it can schedule another executions. So here it's scheduled 3 executions: message 3 on contract 2, message 2 on contract 3, and message 4 on contract 3. And then what happens? They are executed one by one, never in parallel. They are executed one by one. And after, in the first case, I execute the message 2 on contract 2. When the message 2 is executed, fully processed, it just gives back information to the blockchain, that execution is done. And what happens next? Next message is processed. But while sending the message from the contract, contract one processing the first message, I can tell it to reply, send the reply message when the sub-message is processed, basically. And what does it mean? When the message, another message, message 3 is processed by contract 2, the message, after sending the response to the blockchain, that message is processed fully, blockchain sends the reply message to the first contract. And this reply message is where anything which is to be processed after the sub-message is finished happens. Yeah, I mean, I know it's kind of convoluted. You can look at the repo, it is like explained in detail, but there is this flow that I send this message 1, I scheduled message 3 to be executed on contract 2 here, I told to reply on success, and I provide the ID. And this ID would be sent back by the blockchain with the reply. That's very important because there's this thing that when we process the reply, we don't know the original message, we don't know anything about the state when the message was originally sent or when it was finished processing. We just have an ID, and we need to remember the state somewhere in the contract and then refer to it, sometimes via ID. And the flow can be very complicated in terms that we can send a sub-message from replies, we can send another message, sub-calls in, recursive way, but I will not, go in details through this diagram. You can take a look there. For now, I would like to go into the code, actually, because it's enough of theory, I would say. So let's take a look at the contract. Here, we have two contracts. We have donation peer and donation manager. Peer should be the easier one. It is. Okay, sorry. No, peer is the easier one. We can take a look first on HackATOM. So in smart contracts, there are a couple important things to put there. First of all, we need crate type to be CDY library. And this is because our WASM smart contracts are the WASM dynamic libraries. They are not typical Rust binaries, they are dynamic libraries. It is also often that we add the error library crate type, which is typical Rust library to be used as a dependency, for example. We often want to use contracts as dependencies, so we do that. Note that we create a feature, which is library, and I will tell about this in a second why I do that here. And I use a couple things here. The Cosmos stood, the standard library for Cosmos. CosmWasm Storage Plus, which is the utility to access the Cosmos contract state. Std, which is kind of obvious, we want to serialize messages. And multitest, because I want to test our contract. So I want it to be there. And multitest is basically the utility to test contracts using the blockchain simulator environment. So go back to peer and go back into sources. And let's start maybe with messages we would have in this contract. And let's start with instantiate. While instantiating the peer, I would need owner of this contract. So this is the one who can withdraw money from it. And I added two additional configuration state. Incremental donation is minimal donation, which is needed to increment the internal counter, which is how much part of the donation someone would get on donations split. Yeah, so this is this minimal donation for that. And collective ratio is telling me how much of the donation is left on the peer itself and how much is forwarded to the collective, so to the other peers. And this is decimal because it's part of how much is sent to the manager contract basically. So this is what I do, what I take in instantiate message. On execute message, as I showed before, there are two actions. There is donate action. I do not take anything because I send funds with the message itself. I do not need to do this on the message. It's managed by blockchain. And then I have this withdraw function to withdraw money by the owner of the contract. And then I have a couple query messages. They are just, things I made to ask on the contract. I can ask the contract who is an owner, who is a manager. Manager is the pool who created him, the manager contract who created this peer. I can also check for how much donations are pending, which is basically querying for the state of this contract, and can ask for configuration and how many donations went through this peer. And this is important because I can use this donators query when I am splitting donations in manager. So manager could use this donators query to figure out what is, how much to give to this peer. And for every of those messages, I typically create the response structure to have some way to respond. Couple things to keep in mind when creating messages for CosmWasm. We want them always to be serializable and deserializable by SERDA because those messages are just JSONs. We need to work with them. We typically also want debug, clone, and partial queue if we want to test on them, on those contracts, because, utilities thing. And we often add this SERDA rename all attribute. It is because without that, the messages would be serialized as they are here. So what does it mean? The owner structure, the owner message would be like starting with capital letter in the JSON. And we typically don't want to do that because it's more idiomatic in JSON to have it, lowercase. So because of that, we use this rename all to make sure by SERDA that everything is properly renamed to lower cases. Yeah, and another thing I need you to take attention to is this curly braces here, which are not needed by Rust at all. You can have empty enums not having any curly braces here, but it is for SERDA. Without those, the owner query here, for example, would be serialized to the string, just a string. On the other side, the spending donations, for example, because it's object with some structure, it would be serialized to an object with a single field called pending donations with the fields like denom here. To make this more unified, we use this curly braces, so it tells SERDA to serialize it as an object, not as a string. So this owner right now, because it has this curly braces, is serialized as another JSON object with single owner object. It would be an empty object, but with owner field name. Okay, so this is how we define messages in CosmWasm. And then I would like to go, before I go to the contract implementation, I would like to go to the contract state. And what I have here, I decided to keep two distinct entries in the state. You can see that I have two items, one with some state structure, one with the address. I used those item utilities that are taken from CW Storage Plus library, and when I was starting with CosmWasm Smart Contracts, I was kind of confused what are those items or maps for. So they are not storing any data. Any data in the blockchain are stored on the blockchain, not in the contract. And you will see that we get a particular depth argument to interact with blockchain state. The problem is that the blockchain is storing all the values like key value pairs, and there is no fancy things like serialization involved there. It's just, you know, string to string mapping. Because of that, we introduced the CW Storage Plus crate, which provides the abstraction layer over the storage. So we use this, so we don't need to remember what exact string key we use to store the actual value. It also handles any serialization, deserialization, non-existing values for us. So this is just abstraction layer over the storage. And here we are using item, which means there is only single value of this type on the blockchain. What's interesting here, I splitted state to address and the state, and the reason is that whenever we use state, we most typically use the whole state. It's very rare that we want to use only donators or we need to use only collective ratio. We are using this while we are doing the donation flow, and we use all of that. So I decided to keep it in one variable. Another variable is the address, and that's a kind of a different story because I use address in completely different flow. I use the address, which is the owner address. I use this only on white jowl flow to check if the sender of the message is the owner. There is an argument to extract the donators from here, and the reason is you will see later that I actually always read the whole state, but I would modify only the donators. So storing something on blockchain, reading something from blockchain is expensive, gas-wise. So I want to minimize how much data I am, you know, sending to the blockchain. So to do that, I could actually extract the donators to another value. So when I am storing the updated donators, I do not need to store the whole state. I can store only the single data. But I decided not to do that in this case, probably for simplicity. And now it's time to go to the contract itself. I start with the leap RS, because here I have defined entry points. And I have, on this contract, it's kind of simple. I have 3 entry points, which is instantiate, execute, and query. And yeah, go one by one. Instantiate is the entry point which is called exactly once when the smart contract is created. So it's like construct of our smart contract, and its purpose is mostly to initialize the state. The other one, execute, is responsible to perform like standard execution messages. So as you can see, I keep those entry points very simple. For instantiate, I just forward to some instantiate function. You see this. For execute, I just do the dispatching on the message, but I never do any logic in my entry points. I want to keep them very, very simple. So as you can see, I just check if there is donate function, donate message sent. I just, you know, I just call particular functions. Same for query. A very important thing that for queries, I return the binary type from the contract, but my functions would actually return the actual message types I created, not binaries. So I also use this query entry point to just call this to binary function, which takes anything which is serializable and puts it to binary. And I would like to go through those entry points and take a closer look to the signature. So every function and any entry point would have this depth argument as the first one. And depth is basically the window to the outside world. Okay, maybe I can go. Sorry for that. Yeah, you can go to docs RS. here I would quickly look for depth mute. So this depth type gives us the storage field, which allows us to work with the storage. As I said, storage is stored on blockchain, and this is the entry point to modify it to read the state of the current contract. I have also this API thing, which is providing us some helpful functions, for example, validation of the given address and so on. And query is the object which helps us querying data from the outer contracts. We use it either to call the contract queries or to just look into the contract state. For example, we can read directly from contracts. We'll see that in the example. We can also query another things like, for example, bank. We can query for how many tokens is available from the contract, and I think I use it also here. So this is depth. You can see that for query, there is no depth mute, it's depth. And what is the difference? The difference is that if we take the depth type, we cannot modify the contract state. And queries never can modify the contract state. It is only for querying, it's like completely constant. Both execute and the instantiate can actually affect what is stored on blockchain by its nature. Another thing is environment. I do not use it in instantiate, I would use it in execute. And environment is a type containing some information about the blockchain state. It tells you what is the current time in the blockchain, how height is the blockchain, how many blocks are there, and also what is your current contract address. So you can directly relate to your address, you don't need to send it every time. Also there is this info type, which is passed to some of entry points, and this is like meta information object containing some special data sent with the message itself. You would have the message sender, where you never send the sender in the message itself. It is validated by blockchain, and you can always be sure that whatever is in info sender, it is the true sender of the message. There are the funds, the native tokens sent with the contract, so you also know that the contracts, that the funds sent are the actually sent. It's everything validated by blockchain. And the last argument would always be the message itself. Almost always reply is a bit different, but I would tell about reply in a second in a different contract. So as you can see, execute and query entry points are pretty much similar, except that a query cannot depend on the message meta information. There is no message info on the query entry point, and it is because funds cannot be sent there, and query result is public and should not depend on who sent the message. Basically, those information are completely not needed on query. And yeah, another thing is the result of the functions. So most entry points, and I think that all entry points except queries would return the response type. And the response type is the type which is very closely related to this actor model. We put there every message which should be executed after the execution is completed. We put there any information which should be returned to another contract and so on. So this response type is just like actor model handle, basically. And I said that all entry points besides query return that. Query just returns the binary information it returns, because the query is not, the query entry point is not working as an actor in the actor model. We can, query contract just while working on some other execution. And one thing you should also take close attention to is this entry point attribute. Why do you have it? Basically, CosmWasm smart contracts are compiled to WASM. but WASM itself is not working with like complicated Rust types. We cannot send depth mute from the WASM ecosystem directly. We can only send pointers, some integers, and things like that. So to work around that thing, we just create like high-level entry points, like instantiate, taking all those fancy attributes. But entry point decorator, I would say, attribute is a procedural macro which generates the actual entry point for you. The actual meaning the one which would be able to be called from the WASM ecosystem, using only those pointers and stuff, and the entry point would wrap all those stuff in the nice Rusty API, and then it would basically call the instantiator or the entry point. So now let's go briefly to the contract itself. Instantiate, very simple, and I am showing it on here only to show you how to create instantiate things, what to think about. First of all, I always want all my state to be instantiated, initialized. So this is what I do in instantiate, I initialize the state. And this is basically all. I don't do anything else. More interesting is the execution function, and I create separate module for execution functions. And let's start with the withdraw execution. How do I implement that? It is the simple flow, so I need to load the owner on the contract from the storage, because contract knows who is its owner. I instantiated it on instantiation. And then I just check if the owner is the same thing, the same address who sent the message. If it's not, I just return an error, because I can't handle one withdraw if there is nothing to withdraw. I mean, there is wrong owner. Also, when everything is okay, then I need to query for all my tokens for this contract, and I would use this environment variable here, where I just check the contract address, my self address, and I ask the bank module with this query, how much tokens do I have? Right? So those are my donations, which are collected since the previous withdrawal. And what I do next, I add message to the response to be executed after the execution is completed. And the message is the bank message, so the sent tokens sent order. When I want to transfer tokens from my contract, which is always the source for the sent message, to whoever is the sender of this message. We already verified that sender is the same as the owner, and I need to tell what tokens I want to send. I want to send all my donations, so my amount is my donations. Also, what is nice things to do is always add those attributes, and attributes are basically logs from executions. I don't like to use them to transfer data. Sometimes we do that, but it's way better to use data for that, the proper field. But I treat attributes just as logs, and the sender of the original message would collect all the attributes set by every sub-execution, and he can basically trace what happened on the blockchain. And this message, this bank message, would be executed right after this execution is completed. The withdraw execution is completed to transfer all the tokens. And now let's go to this a bit more complicated donate thing. What I do here, first I load the state, because this is something I store my counter in. I store all my metadata I need to work with, and then I need to check if I want to increment the internal counter, because I increment it only if funds sent with the message is basically more than the by this incremental donation in the state. So I just go through all the funds sent here and I check if any entry in that funds is of a proper denominator and has enough amount. The funds is just a vector of coins, and coin is denominator and amounts of those coins. And it's guaranteed by the blockchain that every denominator is only once in this map, so we can just going through that. It is the useful crate called not here. Go to docs.rs. CW utils, which has couple helpers to work with funds. For example, non-payable, some must pay and may pay functions. You can go through this because it makes working with funds easier. Here I just iterated to check if there is proper donation of the denom I expect here. And if I want to increment the state, I increment the state and store the state. If I do not increment it, there is no reason to store the state, so I minimize the data transfer to there. And then what I need to do is I need to split the donation into two parts. One is the part which I leave on the contract, and I don't need to even store this, but I need to calculate the part I want to send to this manager contract to be split between users. So what I do, I just iterate through all the funds I got there, so all the tokens I got sent, and I just map them. So I just multiply the amount of the tokens sent through collective ratio, and this is how I keep how much donations I send to the manager, and I simply just create the execute message. So it's sent to, so the manager contract is executed. So the execute message is just like a bank message, but instead of scheduling sending funds to the contract, it schedules execution. So I schedule execution of the donate message. So it's here. I need to call to binary because the message is basically base 64 encoded message. And then I need to set the address I send to. I send it to my manager from the state. And also I can send some funds. I send my collective donation funds, which are sent here. And again, I send the message. It will be executed right after the execution is finished and because I use this at message as before, I would not get any reply here. On this pure contract, I never got a reply. I never handled the reply. So this is the simple contract. Now let's quickly go to this more complicated, a bit more complicated manager contract. So here, messages are pretty much the same thing. So I have some instantiate message. Very important thing that on instantiate message, I need to pass the peer code ID. And what is that even? So when we create our smart contract, we compile it to WASM binary. Then we upload the binary, the WASM file to the blockchain. And it is not a contract yet. It is just, the reference code which handles the execution, instantiate, and so on. And the contract is created only after the instantiate message is called. So when we instantiate message, we need to send the code ID and the instantiate message. And yeah, with that, the contract is created. And because our manager contract would create other contracts, we need this peer code ID, so we know what to instantiate basically. And also we give this incremental donation and collective ratio just to forward it to the contract basically. Execute message, nothing fancy here. Query, nothing fancy here. So let's go back. State. And in state, there are three things. First, config, and this is a very simple thing. the same thing we had in the peer contract. I would not talk about this thing. But there's members, and members here is a map. And it should not be a map, but I try to simplify things. As I told you before, blockchain is just a key value pair, key value storage. Yeah? And if we would want to store like multiple values which are connected, what we would need to do, we would need to prepare like distinct key for every entry. I keep it map. I mean, and this is exactly what this map does. When you would use the map to store something on contract or read something from contract, it will use this this members string we created with, and it would concatenate the string with the key we are storing on the map. So it does all this keys handling for us, and also authorization and things. What I map here is the peer contract address to its owner address, and I would not need to do that, but I want also the contract the original owner address, the creator address here, because I don't want to allow any creator to add himself twice in the join flow. So that's why I keep it here. But it creates the problem because to determine if the address is in the map, if it's in the value, I would need to iterate through all items, and it is not the fastest things to do. I do it here, but I could not to do that if I would use another accessor. Let's go to documentation. There is this multi-index map. So multi-index map is just like a map, but it allows you to access your data in the map using different indices. So it is what we want here. We would like to use either the peer address or the creator address to access the map. But using it is not so easy. I didn't want to go into that here, but it's worth knowing that there is this thing which is multi-index map to address like this. Here I just used map from peer to address. There is the question why I didn't map it the other way, so the creator address to the peer address. This is because I decided that splitting donations is way more common thing to do, and in this case I prefer my peer addresses to be keys, but this is not optimized at all. To optimize it, I would use multi-map. And there is another thing which is interesting, is the pending instantiation. And this is the thing. I told you that when I break the execution to schedule some sub-message call, then I cannot like start from some place. I cannot like break execution, then do some subcall and then go back to execution. Yeah. After the subcall is finished, I just got another reply message, and I need to handle it from the scratch. But here in the map, I need two addresses to store when the instantiation is finished. I need the peer address, and peer address would be given to me back with this reply message. But I also need the creator address to store it here. And I would store this creator address temporarily in the contract state. So when the replay is called, I would be able to retrieve it. And let's go to library rs, because there is one interesting thing, which is the replay function. So yeah, we have all those instantiate, execute, and query entry points as before, but we have this another special reply entry point, which is called when the submessage we scheduled is finished, but only if we register the message to trigger the reply. So what I have here, I have this dev smooth and environment. As you can see, I have no message info here. And this is because on replies, we basically lose the information about the initial message we got. Reply has no additional context. It has just the reply. And reply contains two things. One is the ID, and this is the ID we sent to the original message, so we can correlate the message we sent with the reply. And the other thing we get is this message result, which is basically execution result. It's very important that this result may be a failure. So it is possible that if we send some sub-message, but we registered on the reply, even if the original message failed, we can still capture the reply, and we can tell that, okay, the sub-message failed, but I want it to be considered be successful. Yeah? It is very important because the nature of the smart contract executions is transactional. So for example, if I sent the bank message previously in this peer contract, if, for example, there are not enough funds on the contract I'm sending from, which is not the case in this situation because I just queried for that, but it may be that the bank message fails, then no state is changed. I mean, even in a state which we change in the execution message, the original message, are not applied to the blockchain state. So what happens is that when we execute the message, we create like temporary cache, and every changes are applied to the cache. And the cache is applied to the blockchain only after all sub-messages are processed and all sub-messages succeed. But if we want to allow sub-message to fail and still apply the changes to blockchain, then we can just catch the failure replay, and we can work on that. So let's see how do I implement it, some messages. Instantiate is trivial like before, but there is this join flow. And this is actually not so trivial. I think it's the most complicated thing here. So how do I implement the join to the pool? First thing, I need the sender of the message because I need to tell the newly created peer contract who is its owner. The owner is whoever is just joining, right? Then I need my config to be loaded because I also forward my whole config to the newly created contract. And then I create the WASM message instantiate function. It is very similar to the execution message, except I have another couple different fields. I have this admin field, which is basically the address who can migrate this contract. That's very important. And admin here is only for migrations. And in this case, I do not even consider any migration flow, and because of that, I do not set admin. So this admin here, I mean, there's often case where there is a notion of an admin in the contract which is managed by the contract itself, but this admin on instantiate was message instantiate is not related to whatever is in the contract. This is only the admin who can migrate the contract. Yeah, I obviously send the peer to the peer code ID, which I want to instantiate. I add the message itself. I can send some funds, and so on. But why I said this is complicated flow? There are two things happening here. First of all, I need to store the sender in my pending instantiation. I said it before, I would need to do that, and the reason is I just want to finish the flow. I want to finish the message handling and send the instantiate. But what I do, instead of sending message, I send sub-message with reply on success. So I tell the blockchain that when this instantiate is finished, call reply on me. And I send the message, I give the message I want to send, and I need to give an ID. Here I set it to the constant. Constant is just one here. And this constant is something I would get back when I would get the reply call, right? So it can be kind of strange because I always send this instantiate with the same ID. So how do I know that my message I just received is the same instantiate I sent for the last time? And this is because there is this rule in this CosmWasm that the message is processed like from the beginning to the end. And since I started this message, this join handling, nothing can happen on this blockchain, on this contract state, unless our sub-messages are completely done. So if I send just a single message, then I know that the next reply I get is this reply to my instantiate. I can get no message back because on failure I would get no reply. On failure it would just break the transaction, nothing would be stored on blockchain, and nothing would happen. But in such case, this pending instantiation would not even be stored, actually. Yeah, I also set some log attributes, but that's not such an important thing. And as you can see here, on this sub-message, I set this peer instantiate ID on the contract. And if we go back to the library, on the reply entry point, I dispatch on this ID, and I use it basically as a message type. So if I see that the ID is peer instantiate ID, then I know this is the response for this peer instantiation reply, and I would use this handler here. Sometimes I would have more than one message I want to handle, and then I can dispatch it here using ID just like message type. And this is kind of common pattern to use. So go back to contract here. Okay, so join is finished. Sub-message is sent. Sub-message is executed by the peer contract, as we've seen before. And the reply is sent. Reply is dispatched to this peer instantiate. And you can think about this join as a single execution. That's why I keep them kind of together. And the first thing I do when I am handling the response here is I am checking the result. And it is kind of redundant here. It is redundant because I specifically set that I want to reply only on success. So I could technically unwrap this. I just do not like unwrap on contract, so I handled this error here in case, for example, I would like to change it in the future, so I want to, I don't know, I want to reply always, for example. Then I have this still working, and I would not produce any crash on the contract, and crashing on contract is not a good thing. Yeah, and when my result is handled, then I get this data, and the data is the field on response. We can even set data on this response type. There is, I think, add data or set data function to set this. This is arbitrary base64 encoded data. So it can be, for example, serialized JSON. In case of instantiate, it is a protobuf object, but I don't want to work with protobuf here. Hopefully, I don't have to. First thing, I check if there's any data because it is an option, it can be empty. But then I use this parse instantiate response data, and this is the function from Cosmos utils. I showed you this crate before. So Cosmos Util is a very useful crate which gives you things like, for example, this helpful utilities to parse this instantiate protobuf object. So I parse it, I check errors. I mean, not the best way to handle them, but some way. And then what I do, I just need to retrieve this pending instantiation I stored before. So as you can see, I cannot like keep data in any kind of memory, but I can store them between execution and reply, and then I just retrieve them. And this is common pattern to do. And then I save entry on my members. So this is how we often handle like multi-stage executions. We just create initial part as an execution message, and then we follow this up with reply. Obviously, in reply we could have another calls. Another sub-messages scheduled. It would be okay to do that. And then we would have another reply on those sub-messages. We would typically differentiate them using some message ID. Sometimes, if we send couple instances of similar messages, we can do some we can store some ID on this message ID, and we then just bitmask it. So part of it is the type of the message on the ID, and part of it is actually identifier of the message we sent. Yeah, so this is how we work with reply. Leave, nothing special here. We just check. We just look for address to remove and remove it. But donate. So also kind of tricky flow. And the donate flow doesn't start here. As you've seen before, we created this donate function on peer, and there was this add message on response, which was calling this donate. Well, this is what happens when external peer called donate on us. First of all, I don't do it here for some reason, but I could check if the message is sent by a proper peer. So I could look for the sender, look in this members map. I would check if there is a key for it, basically. What I do here, I go through all the members, and I query the external contract. And I could do that two ways. First, I could use a query object from this depth thing. I could use this query object to call this donators query, like use the smart query. And I actually think I did this in the previous version just to show it. Let's go here. If we go to the contract here, yeah, not here. Yeah, yeah. Initially, I used on the previous version, I used this query object to query WASM Smart to the external contract, to the peer contract. What is the problem with that? When I do the smart query, I first need to serialize my query message. Then I need to deserialize it again on another contract. It is basically expensive, gas-wise. And because of that, we can use this this, it's in donate, yeah. We can use this query function on the item from another contract. The state here is the object, if you can go to the imports. State is the object imported from the donation peer, from another contract. And I can use this CW storage plus state object or item object to read from it from external contract. What it does under the hood, it uses the querier. We need to even pass it, I think. We need to pass the querier, and it uses a thing called raw queries, which is querying the contract state directly. And this is way cheaper gas-wise because it is just serializing or deserializing data we need to deserialize. We do not need to create any, intermediate messages to do that. So this is something we like to use. The problem with that is that the contract state is not exactly the contract API. The contract API is defined by its messages and, for example, by the query messages. So here I assume that the contract I am using is I assume I know how the state is structured. I assume there is this state in the contract. If someone would, for example, use the other contract here, it may not work. But because my manager contract is responsible for creating those peers, it is basically safe because instantiate contract knows exactly what contract it is creating, know exactly what version contract is creating, and it is connected somehow, one to each other. So this way I just ask how many donators are per contract. I can add them up to calculate totals, and this is repetitive work. I just query for how many funds are on the manager, and why I use this query all balances instead of just relying on funds sent to the donation. It is because when I am distributing funds to my peers, it may happen that division would not be exact. There would be some left over. So to handle that, if there is any leftover, I would just redistribute it in the next call, because I would always use the whole balance stored on the contract instead of just funds which are directly sent. One kind of important thing is that I want to not send, I don't want to send empty messages with no tokens to be sent. For example, if one of the peers has zero weight, it may happen at the very beginning. It is because sending 0 tokens would fail. So to not send message which fails, we just do not send it. Because if the message I sent would fail, the whole transaction would fail and nothing would happen on blockchain. Another way of handling it would be to, instead of send messages, I could send sub-messages with reply on error. And if there is an error, I could just accept it as it is. That's another way of handling it. But here I can just prevent the sending message I know which would fail. And this is how I implement contracts. Basically, how to have communication between contracts. There is another thing I would like to tell you quickly, which is how to test contracts. There are two ways you can imagine. One is to just create unit tests, to unit test those functions like donate. Yeah, I can call donate with some fake environment and check what happens. There is a problem that it doesn't allow for easy testing the relations between contracts. Yeah, it is testing only single function call. It is okay, but it is not enough in most cases. Another way is we could just test it on the testnet. Yeah, we could create the fake testnet, we could send some messages, and we can check what is the blockchain state. The problem is it's not so easy to set up and automate. So what we created is this crate. We call it multitest. We can find documentation like here. And I really recommend to check the multitest crate. If you want to debug your contracts, because there's the problem, debugging contracts or blockchain, I don't think it's even possible. I don't know the way to test contract directly on blockchain or debug it. But what we can debug are unit tests. First of all, we can just print inside of them. And the other thing, we can actually run the LLDB on the test binary, because test binary is our native library. We can easily test it. So what I do here in donation manager and also in peer contract, there is the example of not in contract, sorry, in librs of multitest tests. So how does it work? First, we need our contract wrappers for our contracts, which are objects for multitest, so it knows how to execute contracts. It is basically equivalent of the WASM binary, but for multitest. And if you look at the test, it is kind of straightly manipulating the fake blockchain environment. We create the app object, and the app object is the object being a blockchain simulator. We just store code. So this is just like, sending the code to the blockchain via WASM-D or something. Then we just call instantiate contract. So we do calls on blockchain here, straightly. I send some manager code ID. I send some. The second is probably sender of the message. Then we send the message itself. I send some funds and so on. I can just query the blockchain. So I do not query the particular contract. I query the blockchain. Query was smart with the address. Here is the manager address which I have from the instantiation. And I send the message. And here there is anything which is JSON serializable. I could even use the JSON object from third JSON, I think. I mean, it may bring some problems, but basically anything serializable to JSON can be here. And then I just assert on if the config response is what I wanted to have. Yeah. Same for members list. Initially, I don't want any members on the list. And on the join, for example, test, what I do, I just instantiate the contract. Then, is it the join flow? Oh, sorry. It is. I instantiate the contract on the join flow. I execute join by the member. Then I query the peer address, and I check if the peer contract is properly initialized. So I check if member is an owner. I check if manager is the manager. I check if donators are empty, are zero. Yeah. So basically, I can use the Rust unit test environment to create my smart contracts easily. And even donate flow. Here I left some comment that there is a single donation. As you can see, I just call execute contract donate here. I just donate by donator with 100 of T grades here. And then my member is trying to withdraw money from it. If it succeeds, then I can verify balances on donator, on peer address, on everyone. And this is just like creating unit tests, but with the blockchain stub or simulator, or however you call it. A very important thing is that I mean, this is something we would probably like to work on a bit, but the API to set the funds on the initial funds on blockchain is kind of tricky because we need it to do it while instantiating the blockchain. So we pass this lambda or this closure to application new function. And what we need to do is to call this init balance on everyone. We need to give them some tokens, and because donator needs some tokens to donate, we give him some tokens. Yeah, there are more examples, like more complicated donate flows, but they're basically the same thing. So I just instantiate contracts, I send some execute messages, then I query the blockchain. This is how I test. One thing with multitest I would like to show you is in the peer contract. So when I test peer contract, before I said that I need to instantiate the funds while I initialize the blockchain. So I do it in app new. But it is not always what we need, because when I try to test the withdrawal on the peer contract, I would like to do it in a very pure way. So instead of creating the whole donation flow, I would like just to set some initial funds on the peer contract. But I cannot do that while I am initializing the blockchain. And the reason is because I don't have the contract yet. It's not yet instantiated, it's not even loaded. So what I do, I create the contract itself, I store the code, I normally instantiate the contract, but then I call up init modules. And init modules is like delayed initialization of modules here. And I just init bank balance here. Yeah, and it is everything I have here. I am, I think, below the time, but it's okay. Sorry for this format, but I had some technical issues. Didn't have my machine, so I couldn't show you this whole thing while coding. Maybe it would be more easy to understand, or maybe not. But yeah, this is everything. If anyone have any questions about that, I can answer it. I can also help you with anything regarding Rust or smart contracts or multitest. Just while hackathon, just find me, ask me. I am Cosmos maintainer. Also, we are running the academy thing, so everything here would be taught on academy. This contract is basically what we are creating on the academy, step by step, in a slower way. Here I just made quick review of this contract. Yeah, so thank you for attendance, and if there are questions, I can answer. Yeah, otherwise it's all. So thank you, bye.